Bonjour. Unfortunately, that's where the French stops. Despite the best efforts of my teachers, I'm going to deliver this in English. I think that's for the best. First question I want to start with here is, who's heard of Azul? Okay, most people. That's good. Excellent. So our marketing team is working. Now, what I'm going to talk about here is, as the title suggests, what we can do in terms of improving the way Java applications, or JVM-based applications, I should really say, how they warm up. And so this is something that we've seen really since the history of Java started, almost 30 years ago. Because of the way that the JVM works, we are faced with a performance issue when we start up our application. We've lived with that for a long, long time, and there have been various different approaches to try and solve that. So what we're going to go through is a number of different ways that you can try and alleviate that issue, and how good those are in terms of different types of applications. So we'll see where they fit in terms of your application. So the first thing is to think a little bit about what we mean by the startup of a JVM and the startup of an application. And you can really divide it, as I've done here, into sort of three areas. The first of those areas is the JVM itself. JVM is an application, so when you want to run it, that needs to start up in the same way that any other application would start up. That means you've got to load libraries, you've got to load code, you've got to allocate memory, all that kind of thing. The other thing that happens when you start up a JVM, which you may not be aware of, is that every time you start up the JVM, it will generate a set of templates for the bytecodes that are going to be executed as part of a Java or JVM-based application. I'm going to call it a Java button application just to make my life simple rather than JVM-based application. So it actually generates templates every time. And the reason for that is that you can have different microarchitectures underneath. So even though you're running on an Intel 64-bit processor, depending on which microarchitecture it is, you may have some different instructions that can be used to improve performance. So those templates are generated each time. That's really the only kind of performance benefit you get from the way that the JVM starts up. Then you've got the application itself. So you're going to load the application classes, you're going to do all the verification on that to make sure there are no security issues and they comply to the format they're supposed to be. Then there's going to be initialization of some of those classes. May not be all of them, but you'll initialize some of them. And then you get into your application-specific startup code, executing static void main. Once you've done that, you start running your application, and then you go into this warm-up phase. And that's because we're taking bytecodes, using those templates we generated when the JVM started up, and executing each bytecode in sequence. We're not doing anything really in terms of improving the efficiency of that. Other than those templates that get created at runtime, all we're doing is simply taking each bytecode and executing it every time. There's nothing really good going on there. So if we look at that, basically you can say that the time that it takes to start your JVM plus the time that it takes to get into public static void main, that's the time that it's going to be to first operation. So if you're doing transaction processing, that's how long it's going to take before you can process one transaction. If you take into account the application warm-up time and how long the application is actually running for, then what you're talking about is the time to complete n operations. If we look at the comparison between those three in terms of how quickly they execute, you can really say that JVM startup is fast. You won't even notice that you're creating templates every time. It is very, very quick. It's an application, runs on Linux, runs on Windows. Really, there's nothing that we can do substantially to improve the efficiency of that. Application startup, that's pretty quick. Loading classes, doing all that sort of thing. We can even improve on that a little bit with things like class data sharing, application class data sharing. That enables us to store data about classes that have been loaded in the past and then map that information directly into memory so that we don't have to go through the same process every time. So we can improve that a little bit, but that's still really quite quick. And then you've got this warm-up time, and that's the thing that can take a long time to do. It could be minutes, it could be hours. Realistically, it could be days, depending on what your application actually does. So this is what we're faced with. Now, the other thing that we need to look at is a graph like this, which is a typical Java application. What we're seeing here is the performance of the JVM. So this is not the performance of your application, which could be very much depending on whether you're doing database access or network access, file access, and so on. This is purely looking at what the performance that's delivered to your application code as a result of the JVM. And on the left-hand side, we see it starts off very slow, which is where we're doing bytecode interpreting. Then, as we use the hotspot virtual machine, we do adaptive compilation. JIT compiler and the JVM will identify methods that are being called frequently. It will pass them to the C1 JIT compiler, compile them into native code, and execute them without having to do those bytecodes. As time goes by, that's the green area there, we then pass them to the C2 JIT compiler, which recompiles those methods, but uses profiling information we've collected during the C1 time, and then more heavily optimizes the code to generate the best performing method that we can get. And over time, as we can see, we'll get to a point where we've got a steady state, and that's because we've compiled all the frequently used pieces of code with C2, and we've optimized everything. So essentially in this graph, what we can see is that time that it takes to get to the steady state is our application warm-up time. The other problem that we have is that if we take an application and we run it multiple times, let's say we're doing something like a microservice and we want to run multiple instances of that, what we're going to see is the first time we run our application, we get our graph. Okay, that's fine. But the second time we run our application, exactly the same application, we have to go through the same thing again. So we go through the same analysis of which methods being called frequently. We have to compile them with C1. We then have to profile them. We then have to recompile them with C2. And if we run it a third time, we get the same thing. So there's no memory of anything that's happened in the past. There's no ability to use information from when we ran that application previously to improve the way that the application works in the future. If we look at that, really what we'd like to do is to say, okay, well, let's run our application the first time and then use the information that we collected during that run so that when we run it a second time or we create a second instance of that, we can start immediately from a very high level of performance. And if we run it a third time, we get the same thing. So that's what we would really like to see. Okay, so let's start looking at different ways that we can approach this problem. First of those is, and I do remember this a lot, you see, because I started with Java way back in 1996 when I joined Sun Microsystems, and I can remember that Java took off a lot. And one of the big things that people didn't like about it was slow. And everybody who kind of came up with the idea of how to solve the slowness of Java was, oh, let's just compile it in the same way that we do with C and C++. Well, okay, ahead of time compilation, let's look at that. Why don't we simply avoid using the JVM? Rather than having cross-platform functionality, write once, run anywhere, let's accept that we're going to run our Java application on Linux, we're going to run our application on Windows, whether it's Intel, ARM, or whatever. But we target a specific architecture, specific operating system. Now, that's a traditional approach. If you write C or C++, that's what you're going to do. Okay. This solves us a lot of problems. We don't have to interpret bytecodes. That means we don't have that slow section that we have at the beginning of our graph. We don't have to analyze for all those hotspots. We don't have to do any runtime compilation. And this has a double benefit because not only do we start off more slowly, the other thing that we're having to do is compile code whilst the application is running. That means we're using the resources, the processor and the memory, to do that compilation at the same time that we're trying to run application code. So we take a double hit by reducing the amount of resources we have available to run the application. With ahead of time compilation, we don't have that problem. We can start at full speed. There is no warm-up. It's simply execute the instructions as native instructions. Everything is good. Now this is the Graal native image approach. So quick show of hands, who's using Graal native image? Okay, a few people. Who's using it in production? Okay, a few people. Okay, that's good. So essentially what we can say here is we've solved the problem. Okay, so that's it. We just native compile the code and everything is good. Aha. That would be the end of my presentation after 10 minutes. So no, it's not the answer. And the answer is not so fast. And I mean that in two different ways. The first is that by definition, ahead of time is static compilation. What this means is that the code is compiled before it is run. It's very logical, ahead of time. But if we compile the code before we run the code, that means that the compiler is going to have no knowledge of what the code is actually going to do when we run it. Sure, we can see that there are code paths through our application. We can compile those into native instructions. We can even optimize in a number of different ways. We can do dead code elimination. We can do things like loop unrolling, certain things like that, which are standard optimization techniques. Now, there is a sort of solution to that, which is called profile-guided optimization. And that's been around really since the beginning of compilers. What that says is compile your code statically without any knowledge of what the code is going to do at runtime. Run your application and let it do what it needs to do and collect profiling information as it runs. Store that information and then feed it back into the compiler to give the compiler more ideas about what the code is going to do when it's running. So that's good because it can improve the efficiency of your code because now it knows something about what's happening. But of course, that's still static. There's still no ability to take account of things that change whilst the application is running. Now, to give you some more examples of that and dig into a bit more detail, let's talk about what are called speculative optimizations. And these are very, very important in terms of the JVM and how it can deliver better performance. This particular example is where we're dealing with inlining a monomorphic site. What do I mean by that? Well, I've got a simple class here called animal, and I've used it to encapsulate a value which is color. Because I've encapsulated that, I've made it private, which means I need an accessor method to retrieve that value. Public int get color. Now all that does is return the color. Okay, fine. If I want to use that in my code, obviously I'm going to say my color equals animal.getColor. I call the method to retrieve the value. That's a lot of overhead in terms of the code that's generated because I'm going to have to create a stack frame, I'm going to have to push that out of the stack, I'm going to call the method. All it's going to do is gain access to that field, put it into the return value, pop the stack off, and I've got my value. It's a lot of work that doesn't need to be done. What the compiler will do is it will look at that and say, I can simplify that because I know what's going on in the code. And it can say, right, rather than treating that as a private field, we'll treat it as if it's a public field, and we'll simply reference it directly through the object. That avoids the stack frame and makes the code more efficient. Now, that only works with compilation if you can adjust to the fact that there might be a situation where that method changes. In Java, Java is a dynamic language, not from the point of view of typing, but it is dynamic in terms of class loading. You could load a different class, you could then provide a different implementation of that method, and that would change the way things work. So if you're doing static compilation, you have to be very careful about doing this kind of thing. If you're doing just-in-time compilation, you can do this because you can then, when a class gets loaded that changes the way this works, you can throw away that code and then use new code to reflect what's actually going on. But we can do more than that, and we can do other more complex techniques. This one's about branch analysis. Now, this is a slightly contrived example, but it's good to show what you can actually do in terms of changing the code that the compiler generates. Here I've got a method that's called compute magnitude. It takes a value as an int. I then do a test, and I say if the value is greater than 9, I need to calculate my bias by calling this compute bias method with the value. If the value is not greater than 9, I'm just going to set the bias to be 1. And then I'm going to return log base 10 of bias plus 99. Branch analysis says that what we're going to do is, as we run this code, we're going to profile it and count how many times we go through the true branch and the false branch of that if statement. When we come to compile it, we can look at how many times we've been through those branches, and we can say, if we have never been through the true branch, let's speculate that we're not going to do it in the future. And the compiler can then actually change that code quite significantly. It can say, okay, let's have a new version of this method. We still have to have the test to see if the value is greater than 9. We have a contract between our code and the compiler. We have to respect that. If it is greater than 9, obviously our speculative optimization is wrong, and we have to throw away that code, and we then have to recompile it based on the new set of assumptions. To do that, we use this uncommon trap. That's what's called a de-optimization. This is very bad for profiling and for JIT compilation. But if our assumption holds, then we can eliminate a lot of that code. We know that bias is always going to be 1, that's a fixed value. We're going to add 99 to it, which is 100. We're going to take the log base 10 of that, which is always going to be 2. So let's avoid all that and just return 2. So long as we can maintain that situation, we get better performance for our code because we're doing much better in terms of optimization. So speculative optimizations are very, very important for JIT compilation. And with the work that we've done at Azul, we've actually figured that about 50% or more than 50% of the improvements in performance we get from JIT compilation are down to using speculative optimizations, because we can do different things than we can with ahead-of-time compilation. Obviously, this is good so long as we don't have lots of de-optimizations. And that, if you remember the graph that I showed you at the beginning, you might have noticed there were dips in performance as we did the warm-up, and that's those de-optimizations. The reason de-optimizations are really bad is because obviously we've made a mistake and we have to throw away code that we've already compiled. We then have to compile it again, which means we're using the same resources to compile that code a second time. If we then go back and just do a quick comparison of ahead of time versus JIT compilation, really you can say there's a number of things that are good and a number of things that are not so good. On the AOT side, we have situations where we can't do the same kind of method inlining that we can do with just-in-time compilation because we have class loading that changes things. We can't do runtime bytecode generation. Reflection becomes more complicated. If you've used Graal VM, you know that there's more work you have to do if you want to use reflection. You can't use speculative optimizations unless you do very complicated things where you have multiple code paths to support that kind of thing, which nobody really does. And you can't... The overall performance will typically be lower. And I'm not saying it always is, but typically the performance you'll get from ahead-of-time compiled code will be lower than JIT compiled code. However, you do get full speed right from the very start, and you don't have that overhead of using the CPU to do compilation. JIT is the opposite of that. So you can use aggressive method inlining and other optimizations. You can do dynamic bytecode generation. You can do reflection in a relatively simple way. I don't think anybody describes reflection as simple, but you can do it in a simpler way than you can with ahead of time. You can use speculative optimization, and typically, always have to have that caveat, typically the performance you get will be better because of these speculative optimizations. But you require warm-up, and you require the use of the CPU. So going back to our graph again, if we compare JIT compiled code with static compiled ahead of time compiled code. This is our graph with JIT compiled code. If we look at AOT, we're going to see a graph more like this. I may have sort of overemphasized the difference, but you'll see that the performance will be lower, but it starts off faster. So you eliminate that sort of warm-up time. And then similarly, even if you use profile-guided optimization, that will raise it to a higher level, but typically you will still get lower than you do with JIT compiled code. So when to use AOT? Definitely AOT makes a lot of sense. If you're using things like ephemeral microservices, you're doing AWS Lambdas, you're doing these sort of, I hate this word, serverless computing. It's not serverless. There is a server involved. So if you're doing something like that where you start up a service very, very quickly, you do a small amount of work and then you shut it down. This is great for AOT because you're not going to be too concerned about the overall level of performance. So long as you can get it start up quickly, that effect will drown out any overall difference in performance that you would ultimately get with using JIT-compiled code. The other time when this makes a lot of sense is if you're using things where you've got resource constraints, resource constraints, I should say. If you're using a two vCore container, then you're going to find that one of those vCores has to do compilation at the beginning. That's going to halve the throughput of your application as it does that. So you may again find that for those very small services that it makes a lot of sense to use AOT and Graal VM. Okay, let's look at the second approach to this. What about if we store the JIT compilation data? Now, this is a thing that we've developed at Azul. It's called Ready Now. It's part of our Azul Platform Prime. And so what we do there is we say, okay, let's run the application and take the same approach that profile-guided optimization does. We'll say, let the application warm up, get to the point where you have a steady state, and then we will record a profile of that. And that profile consists of certain pieces of information. All the currently loaded classes, all the currently initialized classes, which may be a subset of loaded classes, all the JIT profiling data that was collected as we ran that application, and all the de-optimizations that occurred. That's very important because, again, we want to try and avoid those in the future. And then what we now do as well is we also take a copy of the compiled code that was generated. When you restart your application, what you can do with the JVM is say, okay, let's use that information we stored in the profile. We'll load immediately all of the classes that we know need to be loaded. Initialize all of the classes that we know need to be initialized. And then make sure that before we get to static void main, we have all of the code compiled, either using the copy that we had before or recompiling based on the profiling information and the de-optimizations that happened in the past, so that when you hit your main entry point, you're running at about 98% of the performance that you had when you took that profile. We can't quite get to 100%. Reason for that, there are certain things that the JVM does internally and certain rules that we have to abide by, which means we can't quite get that 100% exactly the same. But literally, you get 2 or 3 transactions, and you're going to be running at 100% of the performance that you had before. And this is really good because, obviously, if you're doing things like running a trading system and you know that you need full performance at 9 o'clock in the morning, then you can simply start your application at sort of 5 to 9 and have it ready to go. And the reason for that is because we look at our graph again, and I've kind of simplified it here. We have the slope of our warm-up, and then we get to our steady state. That's without Ready Now. If we look at it with Ready Now, we get a much better shape to our graph. Now we've got very fast startup because we do all of the work ahead of time, and we get to that peak level of performance much more quickly than we do without Ready Now. The observant amongst you might notice there's just a little bit of a problem here, which is a little gap here on the left-hand side where there's nothing happening. And that means that your application starts and then it waits while it does all this work of loading classes, initializing classes, and compiling code before it can do anything in your main. So, like I say, trading systems, that's fine because you know when it needs to have maximum level of performance. But if you want to do things where you're going to start up and get high levels of performance immediately, that may not be the best thing for you. But you know, we've done a lot of things to try and push that as far over to the left as possible. But again, for certain situations, it's going to work really well. Other situations, it may not be the perfect choice. Solution 3. What about if we decouple the JIT compiler from the JVM? If we look at JVM architecture, we won't go through all the details of this. Essentially, you've got, at the top, you've got your class loader subsystem, which does all the class loading. You've got your runtime data area in the middle, which is your heap and your stack and so on. And then at the bottom, you've got your actual execution engine, which consists of the bytecode interpreter, the JIT compiler, garbage collector, and so on. So what we did was we said, okay, let's look at that and say, what about if we took the JIT compiler and took it out of the JVM? One of the things we could do here is we can actually take a sort of a package of a compile method. So we compile a method, and we have a set of assumptions that work with that method. So this comes back to what we were talking about earlier in terms of those speculative optimizations. So we compile a method and we list in the method that we've compiled those assumptions that have to hold for this code to work correctly. So only one getColor method, and the value is less than 10. Now, the other thing that we have to understand is that JIT compilation has cost. The fact that you have to run the processor to do that compilation, what you'll find is that there's a cost associated with it. The more you try and optimize code, the more cost is associated with that, because it means you have to use more processing power to find those optimizations and calculate the way to have those work. And what we've done, as part of our Prime product, is to replace the C2 JIT compiler with one called Falcon. And this is based on another open source project called LLVM. So an open source compiler backend code generation project. And what we did was integrate that into the JVM to make it work as a JIT compiler so we could generate more heavily optimized code. That's really good because it lifts the overall level of performance. But as I say, that comes with cost. Now, if you're running on a nice big meaty machine, you've got 64 vCores, you've got 64 gigs of memory, not really going to be too much of an issue. But if you're running on a 2 vCore container, then things become very much more of a performance issue. So let's look at some graphs here. Now, what this is showing is we've got a simple application that we're running on a 2 vCore container. And if we use hotspot, the top graph is showing the performance that we get for our application. And we can see that obviously there's a sort of slope where the application warms up, and then we get to our steady state level of performance. The lower graph is showing CPU utilization. And we can see again that as the compilation happens, we're having to use all the processor capabilities that we have, and we're thrashing both our cores in order to do that compilation and run the application code. But once we get past that compilation, suddenly it drops back down, and we could really, in this particular case, probably get away with running on a 1 vCore container because we're not using both vCores simultaneously, consistently. Now, if we take our Prime JVM and do the same thing and overlay the graphs, we now see something like this, the blue line. If we look at the right-hand side of the graph, that's really good because the blue line is higher than the orange line. That means that we've got better performance overall. And again, on the bottom, we can see that the CPU utilization drops down and we've got the same CPU utilization. The right-hand side of the graph is really good. Obviously, the left-hand side of the graph doesn't look so good. It's taking a lot longer to get to that optimized level of performance, but it's also experiencing a number of drops whilst it's doing that. Even when it gets to that high level of performance, there are drops in performance. And that, again, is down to those de-optimizations. We've been much more aggressive with the optimizations that we do, and those things can then sort of drop out. We also see that the effect on the CPU level is significant for a lot longer time. We see much more in terms of spikes in the CPU utilization. So what we said is, right, let's take the JIT compiler out of the JVM, decouple it. We're running in the cloud, and the cloud means that we have, in theory, infinite resources available to us. So let's take that out and make it into a service. We'll make a JIT-as-a-Service, or as we call it, the cloud native compiler. And that way, all the JVMs for our microservices can share the same JIT compiler service. Now, if we look at our graph again, and we say, right, so this is our blue line where we're running the JIT compiler in the JVM. If we decouple that and we make it into a separate service, what impact does that have on the way that our graph looks? Well, now we've got a green line, and if I drop out the blue line just to make it easier to see, the green line now has a much better profile to it. We've got the same speed of startup that we get with Hotspot and the C2 JIT compiler, but we're getting to that heavy optimization level, which gives us better performance, and we're getting to that very much more quickly. We also see that we don't get anywhere near as many big dips that we saw before. Even better is if we look at the bottom graph, we can see that once we've gone through the class loading phase, that CPU utilization drops off straight away because we're not doing the compilation local to the system. So this is much, much better in terms of the way that the microservice is going to work. Of course, the question about that is, well, hang on, aren't you just shifting the cost away from one microservice into a centralized service? You've still got to pay for the JIT as a service. But yes, but there are other things that we can do there. Because that service is going to be long running, it runs for longer than the individual services. When you start up a new service, obviously it uses the cloud native compiler, compiles using JIT, generates optimized code. When you start up the same service again, new instance, rather than having to compile the code again, you simply just give back the code that you've already compiled because you can remember it. The other thing you can do is you can say, right, allocate lots of resources to this so we can do more heavy optimization. And you can do that in the background. So you take a method, you know you've compiled it once with a set of optimizations. Let's recompile it again, but apply more heavy optimization to it and generate better performing code. Next time the service asks for that code, we've then got that ready, or we could even preempt that and send it to a JVM saying, look, we've compiled this method, now there's a new version available. So there's lots of things that we can do to improve things even further with that. As I said, the other thing we can do, of course, is we can treat a unit of compilation with a set of assumptions. So you can have the same method compiled multiple different ways based on different assumptions that you have from the profiling data. And that way, when an individual service asks for a particular method to be compiled, because it also has that set of assumptions, what we're really doing is almost like a Shazam kind of thing, where we match on a fingerprint to say it's this method plus these assumptions, this profiling data, give it this set of compiled code. If that has a different set of assumptions, a different set of profiling data, give it a different set of code. Solution 4, what about if we combine solution 2 and solution 3? So this is what we did. We called it Ready Now Orchestrator. And essentially what we're doing there is to say, okay, let's take the compiler out of the JVM and let's combine that with a profile that we can collect from a running application. So now we've got the ability to use so when we start up our code, we use the Falcon JIT compiler to generate the code, use Ready Now to have the profile. We can keep all that information in the cloud, and that way we can combine the best of both things to give us, again, much better startup for applications. Solution 5, what about if we save the whole application state? So not just talking about compilation data here. What about if we save everything to do with an application? Now, if you look at Linux, Linux has a piece of technology that's called CRiU, Coordinated Resume in User Space, or as some people try to pronounce it, CRiU. I'm not quite sure how the subtitles are going to take with that, but anyway. So what CRiU does is say, okay, you're running your application. Think of it like your laptop. You're running an application in your laptop and you close the laptop. Now that stops the application from running, doesn't it? When you open the laptop again, the application is in a state that it was before, and you can carry on with your word processing document or your web browsing or whatever. So what we can do in Linux is the same thing for an application. Essentially what it does is to store all of the state of a running application, but in a set of user files. You can think of it very much in the same way, and the reason I put the diagram at the bottom there, it's like time sharing in an operating system. Time sharing in an operating system, switches very quickly between processes to give the illusion that things are running in parallel. It always used to be the case when we only have one processor and one core. And what we would do is we would say, right, run an application for a certain period of time, and then swap it out, store the application, process pointer, store the stack, store the registers, everything that's the state of that, put it into memory, and swap another process in. Run that for a period of time, swap that out, swap things back in again. It's essentially the same thing, but rather than storing the state in memory, we're storing the state in files so that we can restore it at some point later in time, and potentially we could restore it on a different machine. So what we said was, okay, let's do that for the JVM, because essentially you could think of the JVM as just an application, so why not use coordinated restore in user space for the JVM? But we wanted to be smarter than that, There are some limitations that you find if you try and do that, because things like open files, network connections, database connections don't survive too well if you stop them and then try and pick them up again a day later or 2 days later or on a different machine. Coordinated restore at checkpoint, coordinated is the key thing here. So we allow the application to run. This is your Java application now. And then we say, OK, we want to checkpoint that. And we make the application aware that it is going to be checkpointed. That then is able to take action to prepare for a checkpoint, closing files, closing network connections, closing database connections, and so on. At some point later, we want to restart that application. And again, we make it aware that it is being restarted from a checkpoint. It can then say, right, so I need to open that file again. Potentially, it may have done a checksum on the file when it did the checkpoint, so that it can then compare that to see if the file has changed, maybe take some different action based on that, re-establish network connections, database connections, and so on. Then it continues running. So this gives us a better way to restore the application state in a controlled way and a known way. We do enforce that you can't have any file descriptors or any sockets, file descriptors, anything like that open, and it will refuse to do a checkpoint if you have those. The way that this works is very simple. What we do is we've created a very simple API, and the kind of crux of that is a resource interface. You look at your code and you think, right, I've got classes which need to be aware that a checkpoint is being made. So they are the ones that have open files or database connections. You implement the resource interface, and it's got two very catchily named methods that you implement. One is called before checkpoint, and one is called after restore. It should be fairly obvious what those methods do. When the application needs to have a checkpoint made of it, what you're going to do is have those resources registered with a context. The context is essentially the JVM. Context says, OK, register those resources. That way, when you've implemented that interface in those classes, you register them, and when the checkpoint and the restore happens, the VM knows these are the classes that need to have the before checkpoint and the after restore methods called. We can then use the global context, which is really the JVM itself. You can create your own if you wanted to, but most of the time you just use the core context. So then, when you do a checkpoint, what happens is that all of the classes that have this interface implemented will get called in terms of the before checkpoint. Now, the order that happens is the order that you register them in. So it will go through the sequence of classes that you've registered. When you do a restore, it will reverse that order. So it goes down one side and then up the other side. That way you have a clear idea of how things are going to happen. And if you need things to happen in a particular sequence, then that is controlled and you know how that's actually going to work. Does it work? Well, the answer is yes, it does. So here's what we did in terms of a proof of concept. We have generated this, and you can go to our website. You can download implementations of JDK 17 and JDK 21 with CRaC in them. We took some sample applications, and we ran them using a checkpoint and restore. If we take Spring Boot, simple Spring Boot application, and we measured how long it takes to get to first transaction. On the machine that we used with this particular application, it was about 4 seconds. So it was 3,998 milliseconds. If we did a checkpoint of that and then to restore, we could get the first transaction 40 milliseconds. That's 2 orders of magnitude faster. Same thing we did with Micronaut. OK, that was slower. Faster going to first transaction about a second, but again, still roughly 2 orders of magnitude faster in terms of using a checkpoint. Same with Quarkus, about a second to get to first transaction, and 40-ish milliseconds, 33 milliseconds to get to first transaction if you do a checkpoint. We also did XML transform, but that probably isn't the best particular example. So, to summarize then, basically solving the JVM warmup problem. Not one solution will fit everything. In fact, actually, before I do that, there's just one thing I do need to mention about CRaC. So CRaC obviously is a great solution, 2 orders of magnitude faster. But remember that you have to store all the state associated with your application. If you've got a 16 gigabyte heap that is full, then you're storing 16 gigabytes of data plus all the other bits and pieces alongside that. So you can have very big stored state for that. One of the things we try to do, or we do to try and minimize that, is we do a full compacting garbage collection before we do the checkpoint. So we'll try and minimize how much data. We'll only store the data that's actually relevant to the heap, not the whole thing. But it is a limitation. So one solution doesn't fit all. AOT, Graal native image, very good for short-lived services where you're not concerned about the overall performance, and you may not be using things like reflection or bytecode generation and things like that. ReadyNow provides a good way of doing things, so you've got memory of JIT compilation across runs. The cloud-native compiler takes that sort of to the next level, so that you can actually cache the compiled code and reuse it when you're starting up the same application multiple times. ReadyNow Orchestrator combines the best of both ReadyNow and cloud-native compiler. And then CRaC allows you to restart an application from a known point and do that very, very quickly. There is also some other work. I didn't actually put this on my slides. Project Leiden is one that's in OpenJDK. That's a project that's been around for a couple of years now. It has actually started to generate a bit more kind of detail about what they're trying to do. That's looking at different ways of approaching this problem. The current work that they're doing is more of taking the sort of ahead-of-time compilation approach and storing information like that. But I expect to see more information come from that. One other thing to mention about CRaC is we have also contributed that to OpenJDK. It's a separate project under OpenJDK. We would love to see it come into the mainline, but there are a number of issues that we need to solve for that. Primarily, it only runs on Linux at the moment because it's using CRaU underneath. It's not tied to CRaU, and we do have some ideas about how to do it on Windows and Mac, but because they don't have equivalent functionality readily available, it's going to be a lot more work to make it work on those platforms. So there's various things going on there. And that's it. So thank you very much. I have 2.5 minutes if anybody has any questions. I have a question, Dan. Okay, yeah, I'll get back to you.
Hello. Hello, thank you very much for the presentation. Just a question about the ReadyNow part. So you're saying it's effective when you reuse the same application, but most of the time when we have these startup problems is that we deploy a new version of the application. Does it work, or can you reuse part of what was stored?
Yes, so in that case it doesn't. So if you're doing CI/CD and you're doing very frequent redeployments, then what you would effectively have to do is to build build something into your CI/CD pipeline to run a sample application and generate the ReadyNow file for the new version, because we can't use ReadyNow if you change the class underneath. So it won't work in that respect. So if you're doing frequent redeploys, then you would have to have that built into your CI/CD pipeline. It's more targeted at people who are not doing that kind of work. So again, it's one of those sort of like advantages versus disadvantages. There was somebody down there, because you did. Oh, it's the same question. Okay.
Thank you very much. I have a question. Do you have any book for Java performance tuning that we can read and that you recommend to deep dive?
I don't have a book. I mean, there have been a couple of books written about that. The one that I would recommend is Heinz Kibbutz, who's a Java champion. He's based in Crete. He publishes a newsletter, which is the Java Specialist. If you look up Heinz Kibbutz, it's Kabutz, K-A-B-U-T-Z, I think, but K-A-B-U-T-Z, Kibbutz, Heinz Kibbutz. He's a really good guy. He does a lot of stuff about performance tuning. He gets into some very low-level stuff. So I would recommend, he does it for free, so you can just sign up to his newsletter, and there's a lot of really good information in there.
Thank you very much.
I think we have one more question.
Okay. When the profile is stored, it is always in a controlled environment. So it's supposed to be something we know will happen. But what happens when the server crashes and it restarts immediately? We do not have the last version of the profile. So how does it work?
So there are different approaches to that. For example, one thing you can do is you can have a container, and within that container you store the profile. So it's actually kind of hard-coded into it as part of the container. But because if we're talking about ready now here, is that right?
Can you repeat?
We're talking about ready now in terms of the profile.
Yeah.
Yes. So ready now, the profile is just a text file. So where you put that is a deployment choice. One of the things with Ready Now Orchestrator is putting it in a sort of centralized service so that it's easier to access without having to worry about, like they said, if the server crashes, you've still got it in the cloud. So that was one of our decisions, to do it as a service in the cloud to make it easier for that. So yeah, there are different approaches to it. It's just a text file and figuring out where to put it. Okay, I have run out of time, so I will stop here. Thank you very much.